Hello everyone. In this lecture, we want to do some exercises. Basically, we want to prove trigonometric identities. So in order to prove a trig identity, which obviously has a left side and has a right side, and there's an equality sign in between, in order to prove that left side is equal to right side, normally we start with one side of the trig identity. For example, we start with the left side. So you rewrite the left side, whatever it is, and then you start, using other basic trig identities, or you are using the trig identities that are standard and we have proved them in the past. You use those, or perhaps if there's like two rational expressions, you add them up or you subtract them, or sometimes we have to use some sort of factoring or simplifying. Any kind of manipulation, trigonometric, algebraic manipulation you have to do, you do it, but eventually you end up with the expression on the right hand side. So you start with left side, you end up with right side. But the thing is that sometimes one of these two sides is like very, very simple. So let's say tangent of x equals like a complicated expression, for example. If that is the case and you select left side, you're going to start with like tan of x equals, and then what are you going to do? There is nothing there to add, to subtract, to simplify, to factor, to do any kind of manipulation. There's nothing there for you to do. That's why not always we start with left side. So depending on the case, you have to pick a side. Sometimes you select the right side and you rewrite the right side and then start simplifying it until you reach the left-hand side and you prove that right side is equal to left side instead of proving that left side equals right side. Another way of proving trig identities, which you can use it as a last resort, and that is simplifying left side and right side simultaneously. So you simplify a bit the left side a bit, and you simplify the right side a bit, and you keep simplifying both sides, okay? And eventually you end up with the statement, the true statement, always true statement of 1 equals 1. So if you reach 1 equals 1, you're going to argue that because 1 equals 1 is always a true statement, therefore the line above that must have been true. And then therefore the line above that, and then above that must have been true. And this way, working backwards, you're going to argue that the original given trigonometric identity must have been true and left side must have been equal to right side. But I suggest you keep it simple. Don't try those other ways. Just either start with left side, prove that it's equal to right side, or the other way, depending on which side is more complicated, okay? So that's the structure of the proof. There are other proofs as well, maybe other geometric methods or other methods, but we don't discuss them. I have seen students from other countries, they're using other techniques. Any valid mathematical method, as always, is okay, but you don't have to, do it like complicated ways. I have a trig identity right there. I want to prove this trig identity. That's my test question, let's say. So I think about it before I try, and I see on the right-hand side, I see a compound angle expression. Tangent of pi over 4 plus x reminds me of tangent of alpha plus beta. It's right there before your eyes. This is the compound angle formula for tangent, or addition formula for tangent, basically. So I'm thinking if I start with the right-hand side, I can apply this identity that I have already studied in the past. I have proved it in the past. So that's my logic of selecting right side and starting with right side. So I'm going to say RS equals, I repeat the right-hand side, okay? And now I start asking myself, how can I simplify and further push this problem forward? So I'm going to use this identity, assuming that alpha is like pi over 4 and beta is x. So what plays the role of alpha is pi over 4 radian, which is 45 degrees. And what plays the role of beta is x, actually. So cheating from the formula, basically, tan alpha plus tan beta here would be tangent of pi over 4, okay, plus tangent of x. 1 minus tangent of pi over 4, and then times tangent of x. Now, tangent of pi over 4 or tangent of 45 degrees is the same as 1. Everybody knows that. So we end up with 1 plus tangent of x. And in the bottom, 1 times tangent of x is tangent of x. And this is exactly what we have on the left-hand side. And we did prove it, as you see, in like only a few steps. The other identity I'm going to try It says sine of 2x over 1 minus cos of 2x equals cotangent of x. And if you select the right-hand side, as I was saying earlier, what are you going to do with the right-hand side? You can do nothing. You're going to say, okay, cotangent of x. Okay, what about it? At most, you can say it's cosine over sine. That's it. But if you select the left-hand side, you see the double angle in the top for sine, and then cosine of double angle in the bottom. And we have a whole bunch of identities for double angle identities, so perhaps we can use those, right? So we see that it's a wise thing here for this identity to select the left-hand side and prove the left side equals right side rather than starting with right side. I have done like, I don't know, millions of questions over the years. Therefore, for me, it doesn't matter. I can start with any side, reach any side. But for you, you have to start with the side that you can work more on that side, or you can simplify that side, better. So I'm going to select left side here, and I'm going to rewrite it, sine of 2x, 1 minus cosine of 2x. In the numerator, I know the double angle identity for sine. It's right there. Sine of 2 alpha is 2 sine alpha cos alpha. So this is going to be 2 sine x cos x. And then 1 minus, instead of cosine of 2x, I have actually 3 options to select. Okay, I can either use the first form, which is expressed in terms of cosine and sine, or the second form, which is in terms of cosine only, or the third one, which is in terms of sine only. Okay. So this time I'm going to select this last one. So 1 minus 2 sine squared of x. Now, if you ask me, why did I make that decision? Because I had 3 options to select from, but on purpose I select the last one. If you ask me, I'm going to say, well, I knew that there is a 1 in the denominator, and 1 minus 1 would cancel out each other. So 1 minus 1 is 0. So because I could see that one step ahead of me, that's why I suggested that it's better to use 1 minus 2 sine squared of alpha. And how did I know that? I'm not a psychic, but I have lots of experience. By practicing and doing more and more questions, you gain that experience, and then you can start seeing ahead of you. Actually, you can see behind the curtain. You can see 2 steps, 3 steps ahead of you in these kind of proving trig identity questions. So it's not the end of the world, mind you. If you would pick the wrong formula, not wrong, I should say, inappropriate formula, then you would still be able to prove the trig identity, but it would be longer, okay? And sometimes, you would go like wrong way, and you have to just erase and come back. So by experience, I knew that this identity is the best one to select here. So 1 minus 1 is just 0, and negative 2 would be positive 2 sine squared of x. Now, you know that 2 over 2 is 1, needless to say that. And sine x over sine x is just 1. So we are left with cosine x in the top and another sine of x in the bottom. And guess what? The ratio of cosine over sine is actually cotangent of x. And you see how beautifully from the left side, started with left side, we reach the right-hand side. Next identity here, it says cosecant of 2x. I know you're saying OMG at this moment. Cosecant of 2x plus cotangent of 2x, making matters worse, equals cotangent of x. It says prove this trigonometric identity. So I see double angle there, to tell you the truth. So automatically I start thinking of these 3 identities. In the past, in grade 11, we didn't have these kind of identities. So I don't think any of you would select the right-hand side. I don't think any of you would start with cotangent of x and prove that cotangent of x is equal to this sum on the left-hand side, right? So it's just not logical. Therefore, we are going to start with the left side. Cosecant of 2x plus cotangent of 2x equals, okay, now let's see how we can push this problem forward. So instead of cosecant, I'm going to use 1 over sine of 2x. We know that cosecant is reciprocal of sine, obviously. And instead of cotangent, we can write cosine over sine. We just said it 2 minutes ago. So that would be cosine of 2x over sine of 2x in reality, right? If you think about it. Now I notice that sine 2x is the common denominator. So I say, why bother having 2 separate fractions? I just write one of the denominators and simply add the numerators, 1 plus cosine of 2x. And now, in the next step, I see that cosine of 2x is an identity which has 3 forms. Now, which one should I use? This time, I suggest that I use the second form, and I'll tell you shortly why. So instead of cos 2x, I'm going to write 2 cosine squared of x minus 1 all over sine of 2x, which is actually 2 times sine of x times cosine of x. Now, why did I suggest that I use the middle form? Because I noticed I have a 1 here, and here I have minus 1 in the identity. So I knew that 1 minus 1, they add up to 0, they would cancel out each other. Therefore, it was a wise idea to use this middle identity, okay? Now, if you can't see these things yet, it's because you haven't practiced enough. But if you do practice enough, maybe solve like a million questions, then you would be able to see these things better and do the questions faster. So I'm going to continue. 1 minus 1 is canceling out each other. So we get 2 cos squared of x, which is 2 cosine of x times cosine of x, if you think about it. And then the bottom is 2 sine x cos x. So if I continue, 2 over 2 is just 1. Cos x cancel out each other. And I end up with cos x in the numerator and sine x in the denominator, which happens to be actually cotangent of x. And that is exactly the right-hand side that I was trying to reach. So I started with the left-hand side. I used the known trig identities that I've learned in the past. Maybe I added a couple of fractions. Maybe I simplified, and then I ended up with the right-hand side. And that is the technique of proving these trig identities. These 3 questions I took from the homework exercises. And as I said, you have to try to do as many questions as you can in order to become better and better and better in proving trig identities. Thank you for your attention.